Okay, this video covers a worked example for an iterative solution to find the roots of an equation. I'll just talk a little bit about the theory in here as well. So, okay, let's have a look what we've got. The curve with equation y equals 2 natural log of 8 minus x meets the line y equals x at the single point x equals alpha. First of all, we have to show that alpha is somewhere between 3 and 4. Let's have a look. We've got the graph here. Ignore the yellow lines for the moment. So we've got a value alpha here, which is the value of x at which these lines cross. So what we're saying here is that if we evaluate y for y equals x for the curve, and we get the same value as if we evaluate for y equals x. Okay, that's more or less the definition of the point of intersection. Okay, so since the y values are the same for both of these lines here, then essentially the x value equals, or x equals 2 natural log of 8 minus x. Now I'll not go into that in any more detail. This is sort of kind of essentially what we mean by the intersection of two lines. Therefore at alpha we've got x is equal to 2 natural log of 8 minus x, or we could write x minus 2 times the natural log of 8 minus x equals 0. Right, now if we call this bit f of x and we just work this through, then what we'll find actually is if we evaluate this at 3, we're going to get a negative value. And that's basically because the distance between here and here, this minus this, is a negative number. And if we look on the other side of alpha, then it's going to be positive. And therefore, because these are continuous functions, there must be a value in between 3 and 4 for which, when we evaluate this function, f of x at alpha, then it's going to be 0. So that's really what we set out to prove. So the key to this is showing that there is a solution if slightly to one side of the solution it's one side and slightly to the other is the other side. So negative to positive, positive to negative. Incidentally, what it doesn't do is it doesn't show there's only one solution. We can see in this case because we can see the graphs, but in general, if we look at a function, what it's telling us is there's going to be an odd number of solutions in that interval. Okay, right, I'll leave you to have a think about that. Now the question goes on. Say a student uses the iteration formula x sub n plus 1 equals 2 natural log of 8 minus x sub n in an attempt to find an approximation for alpha. Okay, so we're trying to solve this equation. All right, so in solving this equation, we're actually therefore finding the point of intersection of y equals x and y equals 2 natural log of 8 minus x. And so what we're trying to do is just find a solution that if we put x, if we put our value into there and put our value into there, then we get equality. The equation actually holds. So what can we do? I mean, we could just keep guessing, couldn't we? And and we know it's going to be sort of between 3 and 4. So we could, we could try 3.5. We could try, and then that might be, it might be slightly different. This might be slightly different to this. So we try another value and just keep going. And what we probably do is we'd probably get an idea, so which direction to go when we choose our next value. So we could do that as a slightly structured, but still a little bit random. But we've got a better way of doing it than that, by using iteration. And in the iteration, what we do is we start off with a particular value. Well, it's at the end of that scale at the moment here, 4 it's suggesting. So we start off with 4, and we poke that into there, and we evaluate that. And then we take that as our next attempt. So whatever value we worked out from 2 natural log of 8 minus 4, we use that as our next attempt. Now, with any luck, what happens is what is sort of indicated by these yellow lines. Is we get some kind of homing in on the solution. Now, I'll come back to these yellow lines later. They're called cobweb. It's called a cobweb diagram or a staircase. This is really cobweb because it kind of goes round in a circle. Staircase diagram would go progressively towards the solution. You could get either. So the diagrams are more or less the same. So so that is the approach that we use. So it goes on and says, using the graph and starting with x1 equals 4, determine whether or not this iteration formula can be used to find an approximation for alpha, justifying your answer. Well, what it's really asking us to do is to actually draw this this staircase diagram. I'm going to do that in a minute. So hold that thought. But what we're going to do first is we're just going to pitch straight in and see if we can use our calculator to do this. So so this is the process that we're going to follow. So so what I'm going to do is I am going to, first of all, we need to see this storage locator, the answer and storage locator with the value 4. So we just do that by 4 equals. So that's stored in there. And now we're going to put this formula in, which is 2 natural log of 8 minus x. So 2 times the natural log of 8 minus, well, what we want is the answer, of course. Now, when we hit the equals key here, we're going to get what this evaluates to, and that, of course, automatically go into the answer location on our calculator. So so therefore it's ready again to use this iteration formula again. So let's do that. Okay, so we've evaluated 2.77, etc. Now we've got that's in our answer location. So we're going to reevaluate. We're going to evaluate not 2 times natural log of 8 minus 4, but 2 times the natural log of 8 minus 2.77, etc. Okay, so we're going to do that, and that's going to give us 3.307 and so on. So now we're going to evaluate 2 times natural log of 8 minus 3.307, etc. And basically we just keep going. And as you can see, these are kind of starting to home in on a value, aren't they? 3.15, they've all got 3.15, 3.155. Well, essentially, once your calculator stops changing, then you've got a pretty close solution. What's actually happening, of course, is that the further decimal places that you can't see on your calculator are actually changing if we keep on iterating, and that's as far as we're going to go. And so so that is our estimate for alpha. Now, note it is an estimate because you know, this number looks as if we've got a lot more decimal places. It's probably no end to it. Okay, so that is the iterative, the solution which has been found iteratively. So that is the solution to this particular problem of whether these lines cross, and therefore what is the solution to this equation, x minus 2 natural log of 8 minus x. Right, okay, so that is that's what I've done. Now, we've been fortunate on this one because each iteration on the calculator has brought us sort of closer and closer to the solution, and that doesn't always happen. It depends on your iteration formula. This iteration formula has been given to us, so there's always a decent chance it was going to work. But in other questions, you may well be required to actually construct an iteration formula yourself for the solution or to find the root of any particular function. So so let's just have a look at if we draw this thing here. If we've got the graphs here and we can draw this, it's interesting what we're actually doing. So first of all, if we put 4 in and evaluate 2 natural log of 8 minus 4, the value is actually here, isn't it? We can read off the value here. What was it? 2.77 or something like that. So we're going to try again. So what we're sort of doing really is, well, if we can imagine kind of, because this is y equals x, we're sort of coming down here somewhere. Yeah, so if we transplant that value there onto the x-axis and evaluate again, then we're going to get this value here, right? Which along here is about 3.3, wasn't it? Something like that for the second value. And then, so we're going to go down here and then evaluate again. So, what we're sort of doing is we're kind of going up to the curve along to here. Oh yeah, I mean, actually what we've done is, you know what we've done is we should have gone there, down there, and back up there. But we've saved ourselves a bit of travel, haven't we? We've saved ourselves that, and that. Because when we've hit the curve, we've hit the straight line, then we've just gone up to the curve. To the straight line, curve, straight line. So if we want to draw our cobweb or stroke staircase diagrams, then we can save a bit of travel doing all this bit by going curve, line, curve, line, curve, line, curve, line. Now, if we have an iterative formula that actually converges to a solution, then yeah, we're going to home in on the solution. If not, we'll find actually it just shoots off to infinity. Now, to solve any particular equation, then we have different ways of forming the iterative formula, which you'll see in other videos, and some of those will converge and some will diverge. Obviously, we want the ones that converge, so there's a couple of things that we just have to bear in mind when we're constructing that iterative formula. So this one's being constructed for us. So it's everything's nice and straightforward there. So this approach to finding solutions to equations is in the category of problems called numerical methods. And there are numerical methods for all sorts of things, not just finding roots of equations, but all sorts of things. There is another one that we need to know about if you're doing A-level maths, and that's Newton-Raphson method, which is slightly more possibly sophisticated and robust method, slightly less likely to diverge. So that is the subject of another video. Now, if you come across one of these questions in an A-level exam paper, I do recommend that you give it a go, because these things are relatively straightforward for the marks that you're going to gain from them. So well worthwhile, I think. So hopefully that has been useful, and thanks for listening.